previous chapters that we have studied, we have described motion. How we have described motion in terms of position of the object, on velocity of the object. The velocity, the vector velocity, is the change in the vector position per unit of time. Also, we have described the motion using the concept of acceleration. What is the change in velocity respect to time? Now it comes a different subject, and the subject is not how to describe motion. The subject is what makes to the motion to change. If you have an object that is moving with certain magnitude of velocity in a certain direction, what it will make to the object to change either his direction or his magnitude. And what we will see is that the force acting on the object during the time delta t, force by delta t, produce a change in the velocity of the object, then produce an acceleration. So the way to change the direction of the object is to produce a force, to produce an acceleration. And the magnitude of the acceleration is related with the force with the magnitude of the force that is applied during the time delta t. So the wrong question is to ask, what if you see, for example, a spaceship moving at constant velocity? What makes the spaceship to move with constant velocity? Or if you see, for example, an arrow that was launched moving at constant velocity, what makes the arrow to move with constant velocity? And the answer to those questions is that what makes the spaceship of the arrow to move with constant velocity is nothing. He maintains his constant velocity if nothing happens. And this will be the first Newton's law that we will study. So forces doesn't create motion. What a force do is to change the direction of the velocity or the magnitude of the velocity. Imagine you observe a spaceship in empty space, there is no friction, and you observe the spaceship moving with constant velocity. So, what makes to the spaceship to move with constant velocity? What maintains the spaceship to move with constant velocity? And the answer is nothing. He can move forever with constant velocity, meanwhile there is no forces acting on the object. Meanwhile there is no friction, he can move with constant velocity forever. So what maintains the object moving with constant velocity? Nothing, absolutely nothing. Of course that when we say constant vector velocity, we say that is a vector velocity that is maintained constant in direction and in magnitude. The magnitude is maintained constant and the direction of the vector velocity is being maintained constant. If there is nothing acting on the object, the magnitude of the vector velocity will not change, the direction of the vector velocity will not change, and this is the essence of the first law of Newton's law. So the correct question that we need to ask ourselves is, what causes a motion to change the vector velocity? Now, the first law says, if a body that is moving in an uniform motion, vector v is constant, will remain in motion with the same vector v unless a force is acting on the body. So If you leave the object no acting on them, the vector velocity will appear not to change in magnitude or in direction to an observer. And this observer will be named as the inertial observer. The inertial observer is the observer that when nothing is acting on the object, he will see the trajectory of the particle of the object. He will see that his magnitude, the magnitude of the velocity and the direction of the velocity doesn't change. So, in this case that nothing is acting, he will see the trajectory like a rectilinear line. For example, imagine this object. It's a tennis ball. Imagine that the object is moving in this direction, with certain magnitude of the velocity v. This is the vector v. If nothing is acting on the object, he should move a later time with the same vector velocity, the same direction, and the same magnitude. It will happen forever if you don't act, if you don't make a force on the object. So forces, what we will do, it will change this vector velocity. How it will change? Maybe it will change the direction, maybe it will change the magnitude. So the observer is very important. The observer, we name it the inertial observer. All the Newton's laws are a base that exists an inertial observer. And what is exactly the definition of an inertial observer? An inertial observer is the guy here, this guy, that observes the trajectory of something in a rectilinear line. So the V is like this, the V is like this, the V is like this, and he observed that the direction never change, and he observed that the vector velocity, the magnitude, never change. So an inertial observer is the observer that when nothing is acting on the object, he will observe a rectilinear line, a motion with a uniform motion, a motion with constant magnitude of the velocity, and the direction never change. This is the definition of an observer. So, what happens when there is forces acting? When there is forces acting, the force changes the direction of the velocity. For example, imagine the Earth. The Earth is acting on the Moon. Initially, the vector velocity is like this. If nothing is acting, the Moon will move in the same direction with the same magnitude. But because the Earth creates a gravitational field and the gravitational field is acting with a force on the Moon, the force produces a change in the direction of the vector velocity and maybe in the magnitude of the vector velocity. So forces do not cause motion. Forces, what they cause is a change in the motion, a change in the magnitude of the vector velocity, a change in the direction of the vector velocity. So, forces acting on times produce a change in the velocity. So it's proportional to the change in velocity, meaning that if the force is bigger, the change in the velocity will be bigger. So forces acting on times are equal to are proportional to the change in the vector velocity. You have to see the change in the vector velocity, not only in the magnitude of the vector velocity. For example, this is the object. The object is moving with a certain velocity v sub I. The force is acting during the time t1 until t2 during a certain time. The force acting during the time produce a change in the velocity. And the change in the velocity in this case will be v2 minus v1. So v2 is this vector, this is v1, and what the force has done is a change in the velocity, and the change in the velocity is v2 minus v1. This is the change. What vectors does is a change in the vector velocity. Change in the velocity will be v2 bigger, so now there is a change in the velocity. And the constant k is what we recognize as the mass of the object. So let's go to work with this equation many times. Forces acting on times is equal, produce a change in the vector velocity m by the change in the vector velocity. So from this equation we can see that the change in the vector velocity is the force acting during the time delta t divided by the mass. So we see that the change in the vector velocity depends on the mass of the object. If the mass of the object is very big, the change in the vector velocity is very small. So from this equation, we can see that force equal mass by acceleration. Because if you plug in this delta t divided by delta v divided by delta t is the vector acceleration. So force will be m by delta v divided by delta t, which is a. So force equal m by a. But always think in this way. The force acting during the time delta t produce a change in the vector velocity. In the vector velocity, and the constant of proportionality is the mass. Now we write the second law in the following way. The rate of change of an object velocity, or the acceleration, the change in vector velocity per unit of time, is proportionally to the force and is inversely proportional to his mass. So again, we have our equation. Force acting during the time t is proportional to the change in v. So if the force is very big, the change in the vector velocity is very big. If it's a small force acting during a long time, a long period of time, a long interval of time, will produce also a big change in the vector velocity, meaning the direction of the change in the direction of the vector velocity or the change in the magnitude of the vector velocity. So, if this is the force, and the force is acting, and this is the mass equal to, because the change in velocity divided by the change in time is the acceleration, the change in velocity divided by the change of time is the force divided by the mass, is the vector force divided by the mass. So if the mass is very big, well, the acceleration will be very small. And if the mass is very small, like the mass of an electron, the acceleration will be very big, meaning that it will produce a big change in the vector velocity. So let's go to see here. Okay, the third law is a law that intervene two objects, object 1 and object 2. So between these two objects, they will have an interaction. So object 1 will interact with object 2. Let's say that the interaction is a repulsive interaction. So the object 1 is acting on the object 2 and is making a force the force acting on 2 due to 1, acting on the object 2 due to the object 1. This force, let's say that is a repulsive force. What the third law says is that forces doesn't exist alone, always exist in pairs. If this force exists, there is another force that also exists. This force is named the action, and the other force that exists is the reaction. And the reaction is on the object 1 and have the same magnitude but opposite direction. So whenever you try to push someone will push you in this direction. So for every action force acting on body 2, there exists an equal and opposite force acting on body 1, and this force is the reaction. To see the third law, of course, that the force can be attractive also. So in this case, what we mean is that if the force acting on 2 due to 1 is going in this direction, this force cannot exist by themselves just alone. It exists another force that is acting on object 1 and is going in the opposite direction with the same magnitude. So the equation that in the third law of Newton say is that the force acting on object 1 due to 2 is equal to the same force acting on 2 due to 1 with the minus sign, meaning that is in the opposite direction. So it's important to realize that force acting on 2 is acting on the body 2. This is the action. And force acting on 1 is acting on a different body, the body 1. And this is the reaction. What is first, the action or the reaction? Well, indeed, they are simultaneously. This one exists if this one exists. They cannot exist. In the universe, there is no a force alone. There is in pairs. There is the action and the reaction at the same time. Of course, that also this equation, you can read it like this. The force acting on 2 due to 1 is minus the force acting on 1 due to 2. This equation and this other equation are the same. So finally, what it says that F12 plus F21 is equal to the vector 0. Okay, this is what it says, the third law of Newton. But again, force acting on 1 is acting on object 1, and force acting on 2 is acting on object 2. So the force is 0, but it's 0 acting on the two bodies. It's not 0 acting on object 1, or it's not 0 acting on object 2. The force is 0 acting on the set, on the system of the two bodies. Okay, so let's go now to define the momentum of the object. The momentum of the object is a vector. It contains more information than the vector velocity by itself. The momentum P is a vector and is defined like the mass but his velocity. So the unit of momentum are kilograms per meters per second. The momentum, imagine for example a big car moving with velocity. Let's say that you have, for example, a big car moving with velocity of 10 meters per second. And let's say that the mass of this moving car is 1,000 kilograms. So he's moving in some direction with a momentum, a linear momentum, it say also. Linear momentum m by v. So the linear momentum of this object will be his mass, 1000, by his velocity. His vector velocity will be maybe 10 in the x direction. So his momentum will be 10,000 kilograms per meter per second in the I direction. So this is I have a big object moving. Let's say that I have a small object moving. Let's say that it's a bicycle. A bicycle maybe is 30 kilograms, so with the person will be 50 or 60 kilograms. So what is his momentum if he's moving with the same vector velocity? If he's moving with 10 meters per second in the I direction, the momentum of the bicycle, the vector momentum, is his mass by his velocity. And his mass is now 60, by his velocity is now 10 in the I direction. So it will be 600 kilograms per meters per second in the I direction. So you see, this momentum is quite smaller than the momentum of the big car. So then the conclusion that even if they are moving with the same vector velocity, with the same magnitude and the same direction, the momentum are quite different. In the first case, the momentum is 10,000 in the I direction. It's a big vector, big vector. And the second case is a small vector p. P of the bicycle is a small vector. So these contain more information than only the velocity, because they have the same velocity in both cases, but different momentum. So what we are going to establish now is how to change this vector, how to produce a change in this vector. So this will be the initial momentum of the big car. Later on, the big car will change its momentum maybe in this direction. So this is Pi and Pf. So there is a change in the momentum. Where is the change? You know what is the change. This is the change in the now the equation that we will study is that this is the change in the momentum, and something have done this change. Who has done this change? My car was moving in this direction with this momentum. After certain times, he's moving with a different momentum, different velocity, different direction, different momentum, and the change in the momentum is here. What we'll see that the new interpretation will be the force acting on the time delta t will produce a change in the momentum. So this change in the momentum will be the force multiplied by the time that occur between position 1, when the object is going in this direction with this momentum, and the time when the object is going in this direction with this momentum. So the new equation will be this one, that the force acting during the time delta t will produce a change in the momentum. We will pay attention to the change not in the velocity, not only in the velocity, we will pay attention more on a fundamental quantity, that is the momentum, and we will pay attention to the change in the momentum. And we will establish the second law of Newton using the definition of momentum. Please see this equation again. The force acting during the time delta t produce a change in the velocity m by delta v. From here, I can obtain, divide by delta t, I can obtain this equation that the vector force is the mass by the acceleration. So it's important to notice that m is an scalar. So the force is in the direction of the acceleration, always is like this. So you can write also this equation like this. Force acting on the time delta t is the mass by the change in the velocity, but the change in the velocity is the vector v2 minus the vector v1. Remember what we have said about the vector v2 and about the vector v1 is v1 is going like this, and v2 later is going like this. The change in the vector velocity is this one. So the change in the vector velocity is this vector. This is the vector that v2 minus v1. This is the vector that is here, the change in the velocity. So what we are wondering is if the object is moving with this velocity in this direction with this magnitude, and later on he's moving with this direction with a bigger magnitude, what produced the change in the velocity? And the change in the velocity is produced by the force. The force produced the change in the velocity. So this equation will say that the force acting on the time delta t will be mv2 minus mv1. But mv2 is what we have defined by the momentum, the final momentum, p2. So the force acting on delta t is p2 minus the momentum initial, p1. But this is the change in momentum. So we have a similar equation that says that the force is the change in the vector momentum per unit of time, and of course is equal to m by a. But written the equation in this form, written the equation in form of the change in momentum is more fundamental because the momentum contains more information than only the vector velocity itself. So the unit of force are newtons. What it means 1 Newton? Because the force is mass by acceleration. 1 Newton, if the force is 1 Newton, it means that the mass is 1 kilogram and the force acting on 1 Newton produces an acceleration of 1 meter per second square. So 1 Newton is the force that acting on the object of mass 1 kilogram can produce an acceleration of 1 meter per second square. Now we have to pay attention to this word, net. When we apply this equation, force equal mass by acceleration, we are talking about the net force. If there is 2 or 3 forces, we have to sum the 3 forces like vectors, and the sum of the 3 forces will be the net force. And this is the net force that follow the acceleration. The acceleration is in the same direction as the net force. Okay. 2 newtons, what will mean 2 newtons? 2 newtons will mean 2 kilograms producing a 1 meter per second square of acceleration. But also 2 newtons can be seen like the force acting on a mass of 1 kilogram that produce a bigger acceleration of 2 meters per second square. But also 2 newtons can be seen like the force of 2 newtons that is acting on a body of mass half kilogram that produce now an acceleration of 4 meters per second square. Of course, 4 divided by 2 is 2. But also it can be seen the 2 newtons like the force of 2 newtons that is acting on an object of 1 divided by 1,000. Kilograms, a small, is this is 1 gram. And now this force will produce an acceleration of 2,000 meters per second square. It's an incredible acceleration on a small object. So 2 newtons, the same force, will produce different acceleration to different objects depending on his mass. If the mass is 2 kilograms, it will produce only an acceleration of 1 meter per second square. But if the mass is reduced and it's a very small mass, the acceleration will be very, very big acceleration. So this is second square. Okay, now we pay attention to the net force. When you apply Newton's law, the second Newton's law, you have to be sure that you are taking in account the net force. For example, imagine this is the mass. Imagine there are two forces here acting, F1 and F2. F1 and F2 is acting on the body of mass m. What force should I take into account on this equation? F1 or F2? Well, you have to take it in account the sum. So I have to sum F1 with F2. How do we sum F1 with F2? I place the force F2 on the head of F1, and now F1 plus F2 is the net force. And this is the net force that produces acceleration. This acceleration, A, follow the net force. So, when you have, for example, a body with a force F1 going in the x direction, let's say 10 newtons going into the x direction, and you have minus 10 newtons going in the opposite direction, the net force is the sum. So the sum of F1 plus F2 is the net force. But in this case, because you know how to sum vectors, the sum of these two forces are zero. So the conclusion in this case is that when you have a body of mass m that are acting the total force of zero, the total force of zero will produce mass by acceleration equals zero. Because the mass is not zero, the acceleration will be zero, meaning that the change in velocity will be zero, meaning that the velocity final, the vector velocity final will be equal to the vector velocity initial. So when the force is zero, the net force is zero, the vector velocity is maintained constant, and this is what it says the first law of Newton. So imagine, for example, this case. You have the mass m, you have the force F1 acting, you have the force F2 acting. In what direction will occur the acceleration of the body? In the direction of F1 or in the direction of F2? Well, it will occur in the direction of F1 plus F2. So you have to place F1 here, F2 you move it to the head of F1, you make the sum, and the acceleration of the object is in this direction with which magnitude? The acceleration is the net force divided by the mass of the object. So F net is what it matter. What it matter is the net force. So you always look for the net force to find the acceleration of the object, to find the change in the vector velocity. What are examples of forces? For example, you can push or you can pull. This is a force that intuitive we know about this. Also, another force that we will use in this course is a string. A string it will make a force when the string is in the relaxed mode, in the equilibrium. The force that will do through an object that I will place here of mass m will be zero. So it will produce zero acceleration. It will produce no change in the velocity, so the object will remain at his initial position? Well, it will remain as its initial position if its velocity initially is zero. If not, it will not remain as its initial position. So when you study a string like this, the string, when you displace some amount, the string will produce a force in the opposite direction of the displacement. The displacement goes to the right, the force goes to the left. This is the equilibrium position. So this is the equilibrium position when you compress a certain amount, a certain meters, the string. The force, it will go in the opposite direction of this displacement as the compression. The compression is in this direction, and the force will go in the opposite direction. So to see in another way, you will see that when x is negative, if we put the force like minus k by delta x, so the force is proportional to the displacement in the negative direction. If the displacement is going to the right, like in this case, the force is going to the left. So if we place the equation like this, the force is proportional to k by the displacement. But if delta x is positive, the force will be negative. If delta x is negative, the force will be positive because with this negative sign will be converted in a positive force. So you can place this equation like the F equal minus k by x final minus x initial. You can choose x initial equals 0, x final equal x, and you can use this equation that is easier to algebraically to manipulate, that the force is minus k by x. So if you see the force, when x is positive, so you are in this area, in this part, the force will be negative. And when the x is negative, like here, the force is positive. And this kind of force that is a center force is always going to the center. As you see, when the object is here, the force is going to the left. When the object is here, the acceleration is being produced to the right. So the force is to the right. So this kind of system will produce an harmonic motion, and the object will be oscillating around his equilibrium position. So one force that we will use is the force of the string. The other force will be the force that a rope will make on an object. So this is the mass m. So that will be a force that we call the tension force. The tension force will pull the object up. This tension force is another force. The other force type of forces that we will talk about is the normal force. What is the normal force? So imagine you are in the floor, so there are two forces acting on you. From one side, there is the force of the earth that is pulling you down. So this is the force of the earth that we call the weight. W is a force. And the magnitude of this force is the mass by the value of the vector acceleration, g. So your weight depends on g. So this is the force. Now there is another force. You don't fall down, you don't accelerate it down, because there is a force going up. And the force that is going up, we call it the normal force. And this force is the force that the floor is doing on you up. So this force is the force that the earth is doing on you, while this force is the force that the floor is doing on you. And the total force will be 0, so it will mean that your acceleration will be 0, and it will mean that you will not change your velocity, your vector velocity, if your acceleration is zero. So what is the origin of a normal force? A normal force is an electromagnetic force, and is produced by the atoms of the floor in contact, in interaction with the atoms of your shoes, maybe. So this normal force is an electromagnetic force that the floor is exerting on the person, while the weight is a different kind of force, is also a force, but the origin is a gravitational force, and is the force that the earth exerts on the person. These are mysterious force. They are invisible force, but they exist. So we need to take it into account of these two forces. So this is the normal force acting on the object, acting on the body, and this is the weight acting on the body this is due to the earth. This is the normal force due to the floor. No floor, no normal force. No normal force will means that the weight is acting on you. If the weight is acting on you and there is no normal force, you will accelerate downwards, because the force is mass by acceleration. So you will accelerate downwards, and good luck. Okay. There is another type of force that are friction forces. Friction force, they are also electromagnetic force, is another type of forces, and these forces, they always are acting on the opposite direction of the vector velocity. If the vector velocity is going to the right, the friction force will go to the left. So this force, the origin of this force, is also electromagnetic force, and is the interaction of the surface of the mass M with the surface of the floor. This atomic interaction produces a force that we call the friction force. It's a very difficult force to understand, because the interaction is sometimes very random between the atoms of the one surface with the atom of the other surface, but it exists, this force. You can test it trying to move things on the floor, and this is the friction force. So what are indeed the origin of the forces that exist in the universe? There are four types of forces in the universe. The first type of force is the electromagnetic force. They are produced by charge and charge in motion. Electromagnetic force is one of the fundamental forces of the universe. The other force that exists is the weak nuclear force. The weak nuclear force is a very mysterious force. It explains the decay of some atoms. Is a difficult force to understand. And the other force is the strong nuclear force. The strong nuclear force is the force that maintains protons and neutrons in the nucleus without any repulsion. Proton and proton will have a force of repulsion, electromagnetic repulsion. So the strong nuclear force will maintain the nucleus of the atom, the two protons inside the nucleus and the neutrons. They will maintain, even if they have repulsive interaction, electromagnetic interaction, it will be maintained together, and this is due to the strong nuclear force. It's a force of short range. Is the third floor force of the universe, and the other force is the gravitational force. For the moment, we have a theory that unifies the electromagnetic force, the weak force, the weak nuclear force, and the strong nuclear force. But in physics, we still we don't have the theory of everything that that some people expect to unify the gravitational force with all the other forces of the universe. What it means this is that whatever you see in the lab, in your reality, is because one of these forces is acting. There is no other type of forces that we have detected that, that we need to explain what is happening. There doesn't exist the force of love. The force of love maybe is an electromagnetic force. There doesn't exist any type of force that you can imagine. The type of force that you can imagine is either a gravitational force or an electromagnetic force or a weak nuclear force. We don't have experience with nuclear force. We don't, in our daily life, we don't have any experience with nuclear force. And what is the important thing is that these forces are the one who makes change in the motion of an object, who make a change in the direction of the vector velocity, or make a change in the magnitude of the vector velocity. So the summary will be the three laws of Newton. The first law of Newton says, you do nothing, nothing happens. You see an object not moving, and you do nothing, the object will stay here. At the same position, at the same, nothing will happen. You see the object with vector velocity v, and you do nothing, nothing will happen. So the first law will say, if you do nothing, nothing will happen. That's all. The second law will say that the force acting on the time delta t produce a change in the velocity. And the change in the velocity is proportional to the mass of the object. So the rate of change of the object velocity, or the acceleration, is proportional to the mass. Mass by acceleration is the force. And the third law, it says that for every action exists a reaction that have the same magnitude but different direction. And this is the introduction to Newton's law.